pin. Okay, and then, yes, I will mute everyone else for now. But of course, you can always unmute yourself and talk. So if you have any questions, please don't write on the chat. I can't really follow chat, but if you turn on your microphone and talk, that will be awesome. Okay, so this, can you all see this slide? Chapter 1, data abstraction.
Yes.
Perfect. So this part is just an introduction for you to learn one very important concept. This is about data abstraction. It's this is also a motivation behind object-oriented language, but this is something very important that I really want you to understand what data abstraction is. So I will talk a little bit about object-oriented concept. So what is an object? Why do we use an object-oriented design in our programs? So in C, we were using a non-object-oriented language. So this was something very nice to begin with to programming. So if it's the first language you're going to learn, C is a very nice start. I can guarantee you that one. But along the way, you will be using a lot of different programming languages, and you will see that some of them are object-oriented. Then there is one thing very important about this object-oriented design, where you are really writing programs which are interacting with a lot of systems, and in those systems, you should really have some specifications. You should really know how to use some other people's programs. So it's not always going to be like you are implementing everything, but generally, if you're working in large projects, you will be utilizing codes of some other people. So you need to know how to interact with those software. And these are very nicely documented, very nicely organized, let's say, in object-oriented design. So an object is like, let's just give an example so that you can imagine what is going on with this object-oriented design. So imagine you're going to build, like, let's say you're going to build a building, like an apartment. So an architect, like at the first step, designs that apartment. They prepare this template. So how many floors, where is the, like, how big the living room is going to be, how big the kitchen is going to be, where are they located? All that design will be prepared first on the paper. So you will have an exact template of how the instance of that apartment will be when you build that apartment, right? So that template is called the class in object-oriented design. So that class includes all necessary definitions, all necessary specifications of the object, of the instance that you will be building. And later on, if you want to build an apartment, you just look at the template and create the instance. That instance is called the object. So that object includes all specifications mentioned, like specified, let's say, by the template. But there is one very important thing about this object and class thing, this object class interaction. So when you have that template, I don't only need to like build one apartment. I can build as many apartments as one. So when you have that template, like the class template, let's say in programming, you can create multiple instances, multiple objects from that same class. So imagine, for example, our student registration system. So in your student registration system in Hacettepe University, for example, there's a template for each student. Like template means what informations and what functionalities and each student's document will have on the computer. For example, you will have your name, surname, like birth date, department information. You will have a curriculum. You will have variables to store which like courses you took up to now, which grades you received up to now. So all those information will be stored, will be, let's say, designed in a template. Then when you come to Hacettepe University as a first-year student, when you register, they will just create an instance of that class for you, and they will fill those gaps. Like they will replace the name with your name, like surname with your surname. So you will be just an object for a programming perspective. you will be just an object in that system. Then there will be many people, like many students, like we have more than like 10,000 students, then we will have 10,000 objects, which will have derivations from the same class. Of course, there will be some differences, we will talk about them, but that is the general idea, okay? So all those things will be objects of this. So those objects, as I said, they will have some certain characteristics, which means that you will have some certain variables like your name, birth date, all those information, your age, I don't know, like your phone numbers, your addresses, a lot of information will be stored. And then you will have some behaviors, like those objects will have some behaviors. Those behaviors are generally called functions. So in C, you were implementing functions, but they were just standalone functions. Now in object-oriented design, you can have functions specified, like specific to like some specific objects, let's say. For example, a student system, a student class can have a function to report its GPA. So whenever for example, supervisor of the students logins to system, we can just inquire about your GPA. So we can say, for example, İpek Geçin, just get me the GPA of İpek Geçin, then the system will report us the GPA of İpek. So that is how the functions will work. So you will have specific functions associated with those specific objects. It's not a function that you can call and use standalone. That function will be a behavior for that specific object, and that can only be called with that certain object, right? So that is a very general idea about this object-oriented system. So in object-oriented design, then we will prepare our solutions. We will design our solutions by using this concept of objects. So we will describe the solution to problem. So how we are going to solve this. And then we will talk about, we will do how we can express the solution in terms of the object. So because we will be utilizing again the functionalities and the variables, like the characteristics of the objects, and we can create like multiple models of a solution. It's very important. We will talk about this part later, but there are some features whenever you are designing the solutions. There are some features that you should always keep in mind. So there are three important things. First, I will mention, and then we will talk about some other features of object-oriented solutions. First of all, we will be talking about encapsulation. This is something very important. So this encapsulation, inheritance, polymorphism, we will talk about coherence, a lot of other features soon, but these are the terms that you should always know. So whenever you are talking about this software designs, you should be also talking about how encapsulated your system, how you're using inheritance, how you're using polymorphism, what is the coupling, what is the coherence between the objects in your solution. So those are very important concepts that you should be careful when you're designing a solution. But these are also very important concepts that will make you the preferred candidate for job applications. So when you're in a software, in an interview in a software company, they will ask you about these concepts. So if you're aware of these things, just programming in C and solving everything is not sufficient enough in today's world, especially. Programming is something everyone can learn themselves. So like you can see a lot of Indian people they just type a lot of programs very fast, but it's not enough. Otherwise, all programming people will be Indians or Chinese guys. The important thing is you need to know the algorithms, how you can optimally solve a problem, and how you can utilize those very important features, because these are the key things that will make your software robust, efficient, secure, so that no one can attack, no one can crack the system. So it's very important. So let's give some very simple definitions for these concepts. Encapsulation is the idea of creating objects which combine data and operations. Actually, this is something I mentioned, already in the previous slide. So when you're designing these objects, those objects encapsulate the data associated with them. For example, for a student object, let's say, we said it has the variables, like the data it will store. It has the name, address information, phone number, your curriculum, the grades you received. All those data is directly associated with the object. So the important thing here is that without calling that object, without accessing that object, there is no way you can access that data. So the only thing you can interact with that data is through that object. So they are secure. We will talk about this a little bit later. And then also, it's not the data, but the operations are also combined with this object. So operations means the functions. So for example, there is no way they can access your data unless they use the operations you define. For example, when you're designing a student class, you also define some functions associated with that object. For example, you can say a report GPA function, something like that. And then the only way the other people can access that data is through the functions you define. And all those things are encapsulated in that single object. And all the rules, the way that people can use this object and in their programming is through the operations you design. This is something important. And then for inheritance is you don't need to just build standalone like single classes, but you can also have classes that inherit properties from other classes. For example, let's give some examples. So for example, there's one example here, but let's say there's a class in your program for mammals, and then you will have another class for humans, but humans should inherit some properties from mammals. Because the idea is in the hierarchical system, mammals are on top of humans. So any feature mammals will have will also be in humans as well. So when you're designing a human class, you should inherit all the features or some features you define from the mammals class. But then you can also add more features, more objects, more variables or more functionalities for the humans. For example, in a mammals class, you can say like there will be some common features like their blood type, or let's say if they're cold-blooded or warm-blooded, all those things, and then humans will inherit some of those features that you define. And then for humans, you can say humans will have 2 legs, humans will have 2 eyes. So all those things you can add some extra features for the humans class, but you can also inherit some features from your for your parent class, let's say. For example, student registration example, what we can say is we can have a general template for students, like name, all those things, like phone number, a lot of things. But then we can have more classes. For example, we can say undergraduate students and master's students. Then we have 2 other classes, but these 2 classes, undergraduates and graduate students, let's say, they will share some features from the student class. For example, name, phone number, address. But when it comes to their curriculum, when it comes to the number of years they need to be studying here, then they will have separate features for them. Like undergraduate students will be different than master's students, right? So, but you can inherit some properties, but at the end, those subclasses can have specific features for themselves as well. And then we have this concept of polymorphism. This is something extremely important. So this polymorphism is basically says objects determine appropriate operations at execution time. So this may not be very meaningful when you first hear this, but the idea is the functions can behave differently in different contexts. This thing in your programs, if you have this polymorphism structure, this will solve a lot of problems very easily for you. For example, let's try to find some examples for this. So we need to, so for example, I don't know if you have used this in C before, but there are some functions. So when you're implementing a function or method, you specify the number of input arguments that function will take. So you all did this, right? But in some examples, in some cases, there is a way of using alternative number of inputs for a function. For example, let's say a function is receiving 3 inputs, but if you call that function with only 2 inputs, then by default the function can use a specified number for the 3rd input. For example, if you don't specify a number, the function can use 0. So then this function will behave differently in different contexts. So it will first look at the number of inputs you send. If it's 3, then it will use all 3 inputs. But if it's 2, then for the 3rd number, it will replace that, use a predefined number for the third input. So it's like a simple example of how polymorphism will shape the way your function will operate in different conditions. So you will still have the same code, but the way it will function will be different based on the inputs you send, and it will be determined on the execution time. It is not something you will know before. It will at the execution, it will depend on what inputs you will send. Okay, so there are also some 2 features that we will talk a little bit. There is something called cohesion. So the idea here is when you are implementing a function in a programming language, then your function or module should perform one well-defined task. So the idea is, for example, in your systems, let's say, you will be writing a function to calculate the factorial of a number. Then that function should only do that very simple task, which should be very well defined and clear. So you shouldn't do anything besides that operation in that function. So it should be well named, self-documenting, so that those will be the benefits if you use cohesion, like if you use this one well-defined task. So it will be very easy to use, it will be very easy to maintain, and it will be very robust. So this will be like a measure of integrity and efficiency of a module. So when you have cohesion, so it's like all the functions you are implementing will be achieving one very specified task, and they will only do that specific task. So when you have this, then it will be really easy for us to reuse those functions. It will be easy to modify those functions. You will see all those examples. We will see all those examples soon. And then this is just an opposite of cohesion. So there can also sometimes be some coupling between the objects and the modules of the object. So coupling is how much dependency is there between the 2 functions or 2 modules. For example, if 2 functions are using the same data structure or same data, if they're accessing the same data, it's dangerous, because like one based on the execution time, you may have some problems. Like if you're sharing the same data structure, one can do one modification, get some copy, and in the meantime the other function can do something else on the same data, and they can override before waiting the result of the other one. So those coupling things, those dependence are very dangerous. Also, if your function, if the algorithm you solve, and you will see this a lot, if your algorithm you implement depends a lot on the functions of other objects, then your solution will be sensitive to any changes in those other functions, right? So like if someone else changes the implementation somewhere, then you should be very careful about how we are going to interact with the new thing. Like for example, your phones get a lot of software updates, but you can see they only update some specific functions. They only update some specific parts of your software. But when they update that part, the other part of the software, the other functions you implement, should know how they are going to interact with the new software, with the updated software. And this is due to the coupling between them, of course, but you need to know how you're going to react to the changes in some part of the software. And soon in the next slides, we will talk a little bit about of this thing. And then if there is loose coupling in the system, which means that they're not very coupled, then your software will be more adaptable to change, because if there's coupling, if you change something, then it will have some reflections in the other parts of the software. It will be easier to understand, reusability will be easier, and you will have increased cohesion. So this was why I said this is something related to cohesion as well, of course. And for this part, I will talk about the way of how people deal with these problems, like how they deal with this problem of cohesion and coupling, how you solve this in your problems. But I think this is a good time to give a small break so that I don't bore you a lot for this first hour. But in the next hour, we will talk about what like there is one thing very important people use a lot to deal with this coupling and cohesion issues, so that even if you update some part of the software, you don't really affect the other parts a lot. Okay, any questions for the first part?
Will you share the data PDF? Hocam notları paylaşacak mısınız?
Okay, if attendance is always high, I will be sharing all slides and all software we implement together.
Teşekkür ederim.
Okay, just for you to repeat all the material on yourself.
Hocam ben bir şey sorabilir miyim?
Of course.
Benim kameram yok da şu an.
Okay.
Uzaktan eğitime geçildiği için kamera fiyatları da gereksiz bir şekilde artmış. Ben onu temin edene kadar bir iki hafta kamerasız yüze girsem olur mu?
Normally no. Give me a second. I will pause this recording so that in the meantime. Okay, welcome again. I will continue on the slides. And okay, so can everyone see the slides? Is there any problem? Okay, perfect. So then I will talk about this very important feature that I was trying to mention. So imagine this left-hand side is your program. So you're trying to implement something, some program with some specific objective. It really doesn't matter. And then somewhere along your program, you have, let's say, an array of numbers which needs to be sorted. And you know there's a sort function which already does this. So you don't need to write a specific function to sort the numbers in an array, but there is a function somewhere, like maybe an object of some other class or just a standalone function somewhere, which sorts the array of numbers. So the idea here will be like the way you're going to interact is you will send your unorganized data, like the unordered set of numbers, that array, to that sort function. This will sort those numbers into like an ascending order. Then it will send the sorted numbers back to your program. So this is going to be the basic idea of the interaction. So, but for this, you should have some operation contract. So let's go back to this slide so that I can explain what this operation contract is. So if you're using some other function, if you're utilizing something else that other people wrote, then you should know the operation contracts between that function and your software. So those operation contracts are how you're going to send your data to that function. So like, for example, this can be a sort function which sorts the integers, or this can be a sort function which sorts the like some words based on their alphabetical order. So we need to know what type of input is the sort function is requiring from you and how many number of inputs you need. So for example, here, let's say this is a sort function which sorts integers in ascending order. And this says I can only accept an integer array. So you need to know what form you will be passing your data to this sort function. Then you should also know in what form does this function return your solution back. So for example, we can say this sort function is accepting an integer array, with some specific size n. Let's say it requires 2 inputs. It requires the integer array, it requires its length, and then it will sort that things, just swap the numbers so that it will be in ascending order, and then it will pass this sorted data array back as an integer array. So you should know this operation contracts very well. So you should know how you're going to use that method, how you're going to call it, how you're going to pass your inputs, and how you're going to get your solution back. You should know the limitations. For example, we said this only works with integers. So you should know those type of limitations. You should know the purpose, like what it will be doing. So all those like preconditions, postconditions, so in what form the output will be, in what structure it's going to be. Like, for example, we say it will be in ascending order. It will be sorting, but it will not be a descending order. It will be an ascending order sort. So all those things should be in your operation contract. So if you are utilizing some other thing, then you should know that interactions very well. And of course, like although let's say you know those interactions, there can be some conditions that there are some mistakes. Like, for example, this function says it will be only accepting an integer array. But what if you send this an array of decimal numbers? So how you're going to handle this exceptional issues, exceptional problems. So these are called unusual conditions. For example, you like, just as I said, you send an array of decimals. So you should know, so when you're writing this code, you should know, or you should design how your system will react to these unusual conditions. For example, if you're sending in decimal numbers, your function may ignore that input. Just it will not work, and it will just return the array back. So it will say, I did not do anything. Or it can guess the client's intention. So maybe it will be just, it just wants you to turn those decimal numbers to integers, and then maybe just sort them based on the integer parts. You can return a value that signals the problem. So that is just one other way of addressing this invalid condition. So you can just say report as a flag that will just say to the other part. So for example, if this sends let's say integer and decimal array, floating numbers, array of floating numbers, integers, this can just return a flag number, just indicating that it could not achieve, like it could not perform the task because there is an invalid condition in your input. So you can also mention what type of invalid conditions you have. Like in your, for example, a lot of electronic tools, you will see some erroring signals also in your cars. There are some warning lights. So those are the cases when there is something not working. So just like those, you can have those type of flags that signals the problem. You can throw an exemption. This is not a part of this course, so I will not talk about this one, but this is just very similar to returning a value to signals, but this is something you can handle with programming. So it's very nice that you can learn later. So besides those, this concept, like this separation of information brings something very important for us, which is called abstraction here. So what this does is it separates the purpose of the module from its implementation. So the specifications we give to the other part, like for this sort function, if you look at the sort function, the information this part needs is just the way it will interact. This program does not care how this thing is implementing the sort function. So we don't know which algorithm this part is using to sort the numbers. We only know the way we are going to interact with that software. So this thing is called abstraction. It just separates the way the program is implemented from its interaction. And this is very important, especially for the purpose of data hiding. So for example, I will talk in the next slides in detail maybe, but the idea is in some systems, people don't want to give you their solutions. Maybe they design a very nice sorting algorithm. For example, we have Google sorting algorithm. So when you type someone's, like when you search something, when you make an inquiry, you have no idea how Google finds those documents, right? But you can use it. If you give the right input, then it will return you some outputs. So you know how to do it. You know how to specify some information. For example, you can say file type PDF, so it only searches for PDFs. You can put something in double quotes, which will specify that word sequence should be exactly included in that same order. So you know those interactional tools, but you have no idea how Google is implementing the sort operation, how it's finding those documents, like how it's searching and then sorting, let's say. So we have no idea about the implementation for it. So this is also brings an advantage in terms of data hiding. This is also important for the software you implement. Like you can implement some codes for your systems, then you can only tell people the methods that they can call, how they're going to interact, but they will have no idea about how you implemented that. So this is something very important about information hiding. So this is the concept of walls. If you're beginning the, like if you remember the first slide, this part is called walls. So the idea here is you just build walls around your implementation so that no one can see the context, like the content, let's say, of your implementation, which algorithm you're using, which data structures you're using. This part will not know. They can only see this thing through the slits, like this openings in the wall, which are the interactions that you specify. So this sort function here, for example, specifies the way it gets input, specifies the way it sends the output back, and this is the only information your program will know on the left-hand side, right? Besides that, that entire information is now invisible for these people. And there is a very important advantage of information hiding. And this is something happens a lot in your computers, a lot in your mobile phones, tablets, because you receive a lot of software updates. What happens generally is, for example, there are billions of different functions working in your let's say mobile phone, and then something is changing. Like for example, in your YouTube application, it changed the way it streams the video. But there's an app that you're using to open videos in YouTube. You just search it, write it, and then just play it. So what happens here is that, for example, it changed the way it implements the streaming function. Maybe it changed the way it implements streaming MP4 files in different formats. So this thing is updated, this software. If these interactions are same, then this will not have any effect in your code. So when you have this information hiding, and if you're only communicating through these interactions, what happens is, even if you change the implementation on this side, you don't need to change the other parts in your software, right? It's still going to use the same function. Like for the sort function, I believe that Google updates their search query ranks almost every day. It's updated again and again and again and again, but you have no idea what is going on the other side. You just keep typing for queries and getting responses. But on the other side, although there's nothing changed in your side, on the other side, the entire implementation may be different. But sometimes some software update may also require updating the data, this communication, which is generally a major update, and it will update a lot of things in your program. So that is something not a part of this this course, but of course there are also some cases, although they are very rare. There are some cases where you're going to require major software updates. Okay, so I will not talk about this minimal and complete interfaces. So this is about how much availability, like how much freedom you will give to the other side. So it's like if you're giving the complete interface so that they can access every function, or the sort function can only give very simple interfaces, that like minimal interfaces they require to do the necessary tasks. So if we come to our data structure part, let's say So the main topic of this course, this entire semester, will be the data structures. So on this right-hand side, in your implementation, believe me, even Google, like Google systems, a lot of systems utilizes data structures to implement a lot of these functions, like sort functions, search functions. They are all implemented with very different data structures. Like like you may have like Facebook, like your connections, they're stored in graphs, like very different graph structures. Your search queries stored in huge arrays in very huge dimensions with different structures. So all those nice algorithms utilize data structures. So this there's one concept of abstract data type. This is just the collection of data and set of operations. So this abstract data type concept is the class that you can imagine. So that will be a class, and data structure is just implementation of that class, the abstract data type, within a certain programming language. Like here, we will be implementing with C or C++ generally. So the data structure you will be seeing is like if you're using trees or if you're using linked list in this side to implement the solution of, let's say, the sort function. But again, this part, my program does not have any idea about if I am using linked list, I am using arrays or trees or graphs. This thing doesn't know. But on this side, it's highly likely that you will be using a data structure. I will skip this very simple example. It's really not very important. I will skip these. Okay, I think this is a very brief general introduction to data structures. It came earlier. Can someone talk so that I can see if I can hear you?
Buradayız hocam. Duyabiliyoruz
Okay,
sizi.
perfect. Thank you. Okay, so let's continue where we are left in. And recording, I hope recording is continuing. Yes, everything looks okay. Very sorry again, this was a highly critical call for me. It came a little bit earlier than I expected. Okay, so again, the idea is when you're implementing this type of recursive solutions, then like there are some things we need to be careful. We need to know, we need to decide how we are going to define the problem with like the same problem with smaller sizes. So like just like the dictionary example, you need to know, like you will need to define exact identical problem, but each time it will get smaller and smaller. So whenever you are making this recursive calls, the size of this problem gets smaller and smaller. Like in the dictionary example, each time you make a search call, then each time you're making it smaller, like you're getting half of this dictionary, half of the dictionary again, half, and then it goes all the way to one single page. So that will be our base case. So it's like, we will say, if you keep dividing the dictionary to half, then at some point we will be reaching that base case. So you should guarantee that when you're making the problem size smaller and smaller, you will be reaching the base case. You should have a very clear definition of your base case. You will be defining the identical problem with which gets smaller and smaller in each recursive call. So I hope these things will be more meaningful as we keep working on some implementation. Okay, so there is one example here. This is a very generic example. So the idea is how we are going to implement the problem of taking the factorial of something with a recursive strategy. So let's first look at an iterative strategy. Iterative means you just keep iterating the this thing. Like, for example, let's say we will implement a function which calculates the factorial of a number n. So you know the definition of n. So n factorial is n times n minus 1 times n minus 2 times all the way down to 1. And there is also one very specific case, which means that if you're calculating the factorial of 0, that will be 1. So this is the place where your iterations will end, right? So it will go until 1 for n greater than 0, and if n is 0, then your result will be 1. So instead of this iterative strategy, we can also define this as a recursive strategy. So if you think this recursively, so what we should do is, you know what n factorial is. N factorial is actually n times n minus 1 factorial, right? So the idea here is, in each time, for example, let's say you are calculating 5 factorial. You know 5 factorial is 5 times 4 factorial. So the idea here is, in each recursive call, the size of the problem will be smaller and smaller. Like instead of calculating 4 factorial, 5 factorial, now in the next call, you will be calculating 4 factorial. And then to calculate 4 factorial, 4 is greater than 0. Again, so what you're going to do is, there will be 4 times 3 factorial. So in each call, you will get smaller and smaller. And at some point, you will reach 0, which is the base case for this scenario, where you're going to reach, like the result is going to be 1. So, and then all those results will go back. So like all those recursive calls will return their outputs. You will be multiplying the outputs 1 by 1. And then the final result you will get will be your result for the n factorial operation. So this is just a box trace of how this factorial is implemented. For example, let's say you're calculating 3 factorial. So you know when you say 3 factorial, what is going to happen is it will be 3 times 2 factorial. And then for 2 factorial, the result will be 2 times 1 factorial. For 1 factorial, the result will be 1 times 0 factorial. And this 0 factorial is our base case. So this will stop here. It will not do any more recursive calls, but it will return 1. Then this result will be multiplied by 1. That result will be multiplied by 2 here. This result will be multiplied by 2 here, and then the result of this will be your result for 3 factorial. Is there any problem about this part? This the recursive strategy here? Is there anything you want to ask? Okay, then let's implement some of these things so that we are really sure that we know how to implement this recursive strategies. So I need some volunteers for this part. Any volunteer to help me to program this for example, this factorial problem?
Geleyim mi hocam?
Okay, is it Murat?
Evet.
Okay, Murat, can you turn on your camera so that we see you? Perfect. By the way, can everyone see my code screen?
Yes, we can see.
Perfect. Okay, so now we are going to implement, let's implement in C. We are going to implement a recursive function for factorial. So what is the, let's start, let's say, what is the return type of this function should be, Murat? Can you also turn on your microphone?
Sorry.
What?
Integer.
Okay, so let's say we are going to work with integers for the factorial. So what is the function name we should have?
Let's say fact.
Fact, okay. So, and then we need some inputs, like this function should need some input. Let's, I will just say integer num, let's say number.
Yes.
Okay, and then let's do this curly braces. So here, this is the recursive function we are going to implement. So for this recursive function, so for the factorial problem, we already established the logic. So we first need to have the base case so that if this is in the base case, we should immediately stop calling making the recursive call. But then if it's not the base case, then we can make the recursive calls again. So what is our base case about?
Yeah, this is easy one. It is if n equal to 0.
Perfect. If n is equal to 0.
Yes, return 1.
Return 1. So this is our base case. So
base case.
Whenever you come into this function, like whenever you call this function, if this n is 0, we will immediately, so this num, sorry, this the variable input name was num. So whenever this num is 0, then we will immediately return 1 and we are done. But what if it's not 0? So
Then
it's something
it's
larger than 0. So what do we do?
recursive case. Return fact and num times
Num times.
fact num minus 1. We decrease input size to yani base case'e yaklaşmak için.
Perfect. So is there anyone who has any concern about this solution here?
Yani böyle.
Okay. So this looks
Plus.
like a very nice recursive solution for factorial. Is there anyone here in the class? Please respond if there is anything you don't understand about this solution. It's very simple.
I think
Yes.
we should consider n may be negative.
Okay.
I think we should consider.
You mean having n num to be negative?
Yes.
Okay, so
Wait.
this is something an operation contract we should have. So this is an exception. Like normally, when we define factorial, also in mathematics, we don't care about the negative numbers, right? So we don't take factorial of -5. So this is an operation contract. We should tell that, like in program specification, we should tell people that this program only works with n greater than or equals to 0, right? But if somehow you call this function with -5, for example, then just like I showed in the slides, there are some cases that you can deal with this issue. You can ignore it. You can whatever happens, we will see. Or I need to change this a second. Can you hear me? Oops, I can't hear anymore. Can you hear me?
Yes.
Yeah, we
Okay.
can hear.
Perfect. Okay, so just like I showed in the slide, so you can take some precautions, but it depends on the, but it really depends on like the operation contract you make with the people. So for example, for now we say, I only want a number to be greater than or equals to 0. If it's negative, I don't care. Like we will see what happens. So it will definitely, you can see that it will go into some type of infinite loop here, right? So there's no precaution we take, so this won't work. It will go into an infinite loop because it's not 0. It will keep calling it again and again and again. There is no end. It can't reach 0. We are done. So this will be an infinite loop. This is very dangerous if people call this with a negative number. So one thing you can, of course, do is to take some precaution here. For example, you can say, you can make a signaling function. So you can say if, for example, number is less than 0, you can signal a message. You can say return 0. For example, nothing is
Hocam greater oldu.
Oops, sorry. For example, you can say if number is less than 0, you can just return 0. And you can also say, for example, printf number is negative. Like we can say warning. Right? So, but this is about, again, the operation contract you make. So you don't need to do this. I can't find that. Very interesting. Slash the Turkish English keyboard problems. It really doesn't matter. We can add this later, but you can just say number is negative so that you warn the people and you return 0 as a signaling message to the other function. So for example, here we can say integer n is 5, and then we can say integer result is, I will just call that function n, right? And then printf, so we can say, I think I will switch to English keyboard. I can't find the things here easily.
Copy paste edebiliriz hocam.
Yes. Can copy and paste this entire thing. Okay, so we can just say the result is %e, right? I will just say the result. So here we print the result. Okay. So let's run this, and I hope, okay, wheel failed. There's some, okay, this, we forgot to add this. Okay, I found the keys. Okay, so wheel succeeded now. So it says the result is 120 because we said 5 factorial, right? But of course I can call this with minus 5. Then in this case, it will say warning, the number is negative, and then it will say the result is 0. But actually, you know, nothing's factorial is 0. So this is just a signaling method. So in this part of your program, you can check if the result is 0, then there is an error. You can understand. So these are the signaling methods, but this is not really the part of this this course. So we don't really care. I don't really care about this part. So I will skip it for now. But this is something you should always be careful. And it doesn't really matter how big the number you put in, unless you exceed. We already did. Unless you exceed, I will. So I hope some of you already know the problem there, but I will just put a small number for now, so that we don't exceed the boundaries of integers. So this is the entire logic. So here in our function, by the way, in your quizzes or in your exams, when I ask you to implement a function, don't write this main and test part. Just implement this function, okay? So you don't need to implement this main part. Don't spend any time for this part. You will be implementing this function only. And this is a very simple recursive function to implement the factorial. Any questions about this very simple example? Any questions? Okay, there is no question. Okay, then let's do one more example. Any other volunteer? Can I can pick someone. Jana, are you here?
Yes, hocam.
Okay, is there any way you can turn on your camera?
Okay, bir dakika.
That will be great. Perfect.
Yes, hocam.
Okay, Jana, so let's say we are going to, I will change this. So I want to, so the problem is, by the way, you can also implement in your computers in the meantime. So I want to implement a recursive function which implements multiplication of two numbers, two, let's say, positive integers. So I'm constraining the problem. Multiplication of two positive integers without using the multiplication operation.
Okay.
So for example, let's say I will be having this function should do 3 times 5. So, but we can't use the multiplication operation. So we need a recursive program that can implement multiplication function without using the multiplication operation.
Mm.
Okay.
Okay.
So what should be the input? Like, so we said integer already. What should be the input and output types of this one?
Again, integer.
Yeah, integer. So this will return an integer. What do you want your function name to be?
Mult.
Mult, okay. And then input is again, I will just say, okay. So now we don't have only one input. We have two inputs, right?
Yes.
So we have, let's say, number 1, and then we have another integer called number 2. Okay, so what is the recursive strategy we can use? So can you suggest us something? So we will multiply num1 by num2 without using the multiplication operation. So what we can use here?
We have to use addition, but what is the case?
What?
I'm thinking of the base case. What would it, like the base, what would it be?
Okay. So Jana suggests using addition instead of multiplication operator, but in order to do this recursive call, she needs to decide the base case. So when it will stop, when she will stop making recursive calls.
So it will be like num. So it could be like number. Okay.
Okay, let me ask you some questions and then we will find the answers for all of these together. So what is your addition strategy? So what do you want to replace num1 times? So normally the solution is this, right? Right, so normally this is the solution. But
Yes.
this, so I will just put so what is your solution strategy? Like in factorial, like on paper, like on the slide, you see n factorial is n times n minus 1 times n minus 2. What is the iterative idea here? So
it is to be like number 1 plus a mult of number 1. So, but then like when do we stop?
No. What is the implementation of this multiplication as in like as an summation operation? So what do you understand when I say num1 times num2? So for example, 3 times 5. So how can I write?
So we add 3 5 times.
Perfect. So so you say we add 3 5 times. So we can also do this in the other way around, right? We can add 5 3 times. It really doesn't matter, right?
Okay.
So Jana says we can replace 3 times 5 with adding 3 5 times, right? So you're saying the first input will be the number you will be summing, and then the second number will be keeping the number of times you are going to implement this. So
yeah.
So it's like the second input here, 5 or num2 is the size of the problem, which you should reduce each time, right? So
yeah.
So like for example, here instead of having this adding 5 times, so I can replace this with 3 times 5 as 3 plus 3 times 4. So this is a smaller problem, right?
Yes.
So based on the solution strategy you provided, I can say, okay, so I am reducing the size of this problem to 3 times 4 by adding the result of this with summing the result of this with 3. So this thing, the second part, like 3 times 5, 3 times 4, 3 times 3, it will go down in each recursive code. So what is your base case is going to be?
So it can be number 1 plus mult of number 2 minus 1.
Wait a second, number 1 plus mult of number 1.
Number 2 minus 1. No, okay. Yeah.
So yes, so this is like the result. So this is the strategy. This is the result you are going to implement. So instead of 3 times 5, you're saying 3 plus 3 times 4, right? This is okay. But what is the base case? When you will stop recursive calls?
When number 2 equals 0.
Perfect. So what is your condition in that case? So when number 2 is equal to 0, what you are going to return in this case?
0. Oh, no, 0. 1.
1?
No,
but this is addition. Be careful.
Oh yeah, it's addition to 0.
Okay. So this is the strategy Jana suggests now. Like she says, the base case should be number 2 when number 2 is equal to 0. So whenever number 2 is 0, then she will return 0. But if number 2 is not 0, then she will keep calling the same function by reducing the size of the problem, right? So in each call, we are reducing number 2, right? Is there any problem with this thing? So let's give an example. Num1 is 3, integer num2 is 6. Then I will call this mult function here with num1 and num2. Right, and then the result is this. So let's run this. And the result is 18, which is correct. There is no problem in the implementation. Any comments or any suggestions about this program, this recursive program? Anyone else?
Hocam merhaba.
Merhaba.
Sesim geliyor mu?
Yes, yes.
Birinci variable'ımız 0 olursa sıkıntı olmuyor mu?
Yes, but these are the operation contracts we decided at the beginning. So we said both numbers will be non-zero, like larger than 0. So we say they will be integers with larger than 0. But for those cases, you can take some precautions again. But normally, I always try to define this type of specifications so that you don't need to deal with issues. Okay, thank you very much, Jenna. Then there is one question I have for maybe for someone else that can help me. Like, can you change this base case so that we do less recursive calls? So here, Jana defined the base case as num2 is equal to 0. And then in that case, we return 0. So I want to reduce the number of recursive calls. Can you suggest me a change here, which will help me to reduce the number of recursive calls?
Hocam ben söyleyebilir miyim?
Of course.
num2 1'e eşitse deriz, sonra da return num1 diyebiliriz.
Perfect. By the way, can you also say your name?
Ayşe.
Perfect. So what I should suggest is this should be num1? Yes. So what I should suggest is instead of using 0 as the base case, we can use 1, and then in that case we just return num1. By the way, some other people are also writing to chat. They are also correct. Thank you. But I really prefer talking. Like if you can open your microphone and talk, that would be great. Like as you can see with Ayşe's modification, we are also getting the same result, but this time we are making one less recursive call, which is really very important, like for efficiency. So you need to be careful about these things. And in your midterm and final exam, you will always be having one question about efficiency. So it's not about only implementing the solution. I will say, implement the solution for this problem as efficiently as possible. So in those cases, you will be caring about those efficiency issues, but for now, this is completely okay. Okay, then I promised you one thing at the beginning. I said at the end of this lecture, you will all of you will be able to solve this Hanoi Towers problem with minimum number of loops. So can we implement a solution for Hanoi Towers now? So let's look at the Hanoi Towers problem again. Is there any volunteer, by the way, that can help me to implement Hanoi Towers? There's Ayşe, help me in the previous one. Ayşe, do you want to help me to implement a solution for Hanoi Towers?
Olur hocam.
Okay, can you turn on your camera, please?
Tamam.
Okay, so if you remember this problem we dealt with at the beginning, so this is the general problem. So the idea was moving the 6 disks from pole A to pole C by sometimes using pole B as an auxiliary pole. The rules are you can only move one pole at a time, one disk at a time, and you can't place a larger disk on top of a smaller disk. And I want to apply a recursive logic here so that we will also implement that logic. so that we can move all of these 6 disks to pole C with minimum number of moves, which is 63. So what logic we can use, Ayşe, here?
Yani hocam düşünüyorum da şimdi bir kere şeyi mutlaka belirtmemiz lazım. İşte daha küçük bloğun üstüne büyük blok gelemez. Ona göre
Evet.
düşünmemiz lazım.
Okay.
Tam böyle net sınırlarını tam net söyleyemiyorum. Böyle birazcık ben de deney yapmaya çalışıyorum.
Perfect. Okay, but we need to have, so you need to remember, this is for everyone again, like, you need to remember what is the goal of recursive calls. So like, the first thing you need to decide how you are going to solve, like separate this large problem into smaller problems. So like, for example, what is the problem size here? Can you tell me what is the size of the problem?
6.
Okay, so it's the number of disks, right? So
Evet.
if you think recursive logic, so your goal should be reducing the number of disks you move, right? So that is the, like that 6 is the number that you should reduce in each call. So then how can I reduce that, the problem size here if you think recursively? So the goal here is normally moving the 6 disks to pole C. This is the problem. So how can I reduce the problem size?
Önce yarısı için falan mı yapabiliriz? Yani
That is an option. That is an option, or you can do this one by one. Like you can, like if you think about the factorial solution for the factorial problem or the multiplication problem. So what we do is we only reduce the problem size by 1 in each iteration. Right? So for the factorial or multiplication, we did the same thing. You can also do the same thing here. So you should reduce the problem size by 1 by making one recursive call. So like if you reduce the problem size by 1, which means that instead of telling move 6 disks from A to C, you should say move 5 disks.
5 tane.
Yeah, okay. So where should we move the 5 disks?
Yani işte tavır 3'e. Onu sormuyor musunuz?
No, like the main problem is we should move 6 disks to tower 3.
Evet.
A smaller version of this will be moving 5 disks to tower 2 temporarily, moving this bottom disk to tower 3, and then moving those all 5 disks back to tower 3.
Tamam. Önce 5'ini tavır 2'ye bizim taşımamız lazım.
Okay.
Ondan sonra da en alttaki en büyük diski tavır 3'e taşıyıp problemi öyle mi çözmemiz lazım? Muhtemelen öyle oluyor.
Yeah, that is one strategy. So one strategy we now have is we will move this first. So instead of like this is you should understand one thing. But like when I say move 5 disks, this is not something a valid move. You can't move 5 disks. But this is another problem. This is not something we will say you move these. It's just let's say it's just the strategy we are using for now. So for example, if you remember the summation, like the multiplication that Jana did. So instead of summing 3 5 times, what she did is 3 times sum these 4. It's the same problem, but you know each time it will be smaller. So what I can define here, for example, is instead of moving the 6 disk to tower 3, what we can do is we can move this. We can define the problem as move top 5 disks to tower 2, move bottom disk to tower 3, then move those 5 disks to tower 3. So now, if you look at the problem, instead of solving moving 6 disks, now we need to solve 2 times moving 5 disks. Okay, so now our first problem is moving this 5 disks to tower 2. How can I do
Hı
that?
hı. Yani bunu da yine böyle bölelim. İşte bu sefer de 4 taneyi şeye taşıyalım. Diğer tavra taşıyalım.
Exactly. So
Yani böyle böyle gidiyor.
exactly. So now instead of moving this 5 to tower 2, which is not a valid move, so what I do is I say move this 4 to tower 3, move this 5th one to tower 2, move those 4 back to tower 2.
Evet.
Now what we have is we need to only move four disks to tower 3, right? But this is also not a valid move. How I move this 4 disks to tower 3?
İşte bu sefer de 3 taneyi.
Perfect. So
Evet.
this is the entire logic. Can everyone understand this? Is there anyone having any difficulty about understanding this solution? Okay, no one responds anything, but so the idea is instead of moving the 6 to here, we say we move 5 to here. But in order to do this, we need to move 4 to here, 3 to here, 2 to here, 1 to here. So it's just, I don't even need to think, I just implement this. So now 2 is here, now 3 is here. In order to put 3 is here, I now move this 3 here. So now 4 here, but I need to move this 3 back to here. So I need to move 2 here first. In order to move this 2 here, I need to move this first one here. So it's just, I don't need to think this complex issues. So I need to move these 2 here. So I will move this 1 here first. So now I move this 4 here. So now I move this 5th one into the middle one, middle tower. Now I need to move this 4 back to here, but I can't. In order to do this, I need to move this top 3 to here. I can. In order to make, I need to move top 2 to here. And in order to make it, I need to move the top 1 to here. So this 1 goes here, 2 to the middle row, 3 back to here. But in order to move this 2, again, I need to do one trick. I need to move 1 back, move this back here. Oops, this is that, right? So now I can move this 4th one back to here. Now I will move this 3 to middle row. Again, the same logic. I can move this 3 here. So I need to move 2 to here. Then I can put this one here. So in order to move this 2 to here, I need to move this top 1 here. Then it's the same logic again and again. You just keep doing the same logic. Like if you look at the current size, so what we have now. Now we move, like if you remember how we divided the problem at the beginning, we said move the top 5 to middle row, move the bottom 1 to target, then move this 5 back to the right side. And moving this 5 is the exact replicate of what we have done up to now, right? So this is the very general logic. But now we will implement the code, which will tell us to move like this disk from here to here, this disk from this pole to this pole. So we need to have this type of logic. So let's go back to Xcode so that we can program this. Oops. Can you see my code screen? Ayşe, where did you go?
Hocam hızlıca bir daha anlatabilir misiniz?
Buradayım hocam.
Of course, like, so we have 3 poles, 3 towers, let's say. So let's say you're trying to move 5 disks from tower 1 to, you want to move 5 disks from tower 1 to tower 3. So what I'm going to do is I will divide this problem into smaller problems. So what I will say is instead of moving 5 to tower 3, now I will move top 4 to middle row, middle tower temporarily, move the 5th one to top 3, which is just one single move, which I can do. Then move those 4 on the middle tower to right tower, right? So that is the strategy. So when I do this, instead of moving 5 disks, now I redefine that problem as moving 2 towers with 4 disks and 1 single disk. But I know I can move 4 towers at a time. So I will again recursively call this thing so that I know how to move that 4 tower to the right. Is this okay for everyone? Can everyone understand the solution?
Understand.
Okay, okay. So let's implement this. So I will clean this, everything. I can keep this hello world here. I will say Hanoi for this one, maybe. I will define the input output so that we don't spend so much time for this part. But we will only be focusing on how we can do this. So for Hanoi, I need some parameters. For example, I need the size. I need, let's say, character, just whole numbers. So for example, character source, let's say, character maybe destination, and then auxiliary. So let me first define what I did here, and then we will implement this with Aisha together. So let's say we are going to implement a solution for Hanoi Towers. This will tell us, like, move this from here to here, this here to here, so that we just follow those steps and then we achieve the result. So here I have a character for source. So let's say tower A, destination. In our case, destination was tower C, and then auxiliary is tower B, right? So this is the idea. So here, you remember our solution, but we need a base case for the solution. So what is our base case?
En küçük bloğun elimizde olması, bir tane blok kalması. Yani.
Perfect. So we say if n is 1. So if in this case, if n is 1, which means that I have only one disk to move. So what do? I will just move that disk because it's just one disk. It's within the rules. I can just tell that move this disk from here to here, right? From source to destination. So let's just prompt a message so that we can follow this. Move the disk from, I will say source here, to destination. So maybe we should say character. Right, source to destination. So this is our base case. This is where we are going to stop. So this only says if n is 1, you just move the disk from source to destination. You don't need to even use the auxiliary towers, right? Okay. What if n is larger than 1? What do we do in this case?
O zaman bir eksiğini kullanarak işte recursive fonksiyon şimdi burada yazmamız lazım.
Okay, so what was the strategy? So now it says move, let's say 5 disks from source to destination. So what is the strategy here now?
N-1'i önce şey yapmamız lazım. Auxiliary'e taşımamız lazım.
Perfect. So Aisha says move n-1 from source, right? Source to auxiliary, right? So now destination is auxiliary.
Aynen.
By using destination as the auxiliary place, like helping place, right? So now, like if you look at this, this is very important. So now what we do is what Aisha says is, for example, let's say n is 5. So this says move 4 disks from source to auxiliary, using destination as the auxiliary place, right? And then what do we do? So we move top 4 to the auxiliary row. Okay.
Bunu artık işte recursive bir şekilde yapması lazım. Yani bu sefer 4 oldu. Şimdi 3 taneyi.
But
efendim?
Like this thing, when you call this, it will do this recursively, but this is not the end of our solution. So if you remember the problem, let's say like we have 5 disks in tower A. We need to move all those 5 to tower C. The only thing you set up to now is move top 4 to tower B.
Şimdi en kadarını destination'a taşımamız lazım.
En kadarını, I didn't understand.
Ya n-1 kadarını yaptık ya.
Okay.
Onu aksiyoleriye taşıdık.
Okay.
Şimdi mesela 5 taneydi. Biz şu an 4 taneyi aksiyoleriye taşıması gerektiğini söyledik.
Okay.
Şimdi 5 taneyi asıl destination'a taşıması gerektiğini söyledik mi?
You mean the last disk, only one disk?
Evet,
Only
evet.
one. Okay.
5'inci.
Okay, so now we need to say this again. So we will say move the disk from source to destination, right?
Evet.
But this is also not the end. Because we moved, like, for 5 disks, we moved top 4 to auxiliary. Now we move the last bottom one to destination. So what is the last thing you need to do?
O kalan 4 tane bloğun tamamını da destination'ımız lazım şimdi.
Perfect. So now we will call Hanoi again with n-1. What is the source now?
Bu sefer aksiyoneri sorusu.
Yes. So now they are in auxiliary. Where they will go?
Destination'a.
Perfect. And then they can use the source as auxiliary.
Hı hı.
Move at this. I will just say move at this. I think this is the end. I don't know if we need anything else. So this is the solution for the entire thing. Let's try and see. So let's say Hanoi and let's say 6. I will say A, B. No, the destination was C in our case.
Hı hı.
Using B. So let's run this and see the solution. I don't know what there's all methods, all paths do something. Did we make anything wrong? Definitely we made something wrong. Can someone
Hocam if'ten sonra return koymadık.
what?
If'ten sonra
Okay.
return
Perfect.
koymadık.
Perfect. Done? See? Any other issues? Let's see. Okay, we have a list of moves that we need to make. I think it's very long. Give me a second. Okay, let's reduce the problem size. It will be very long to implement this. So let's just say for 4. But of course, this will be solving for any n. It doesn't matter. So this is. Can you see my screen, by the way? Can everyone see the solution here?
Yes, we can.
Okay,
Görünüyor
so
hocam.
what I will do is I will also open this game here. And then I will reduce this. So I will change screen share to desktop view. Can you see both these towers and the solution strategy here? Oops.
Yeah.
Okay, so Ayşe, can you read the steps one by one? So I will just implement that steps.
Tamam hocam. A'dan B'ye,
Okay,
A'dan C'ye,
okay,
B'den C'ye,
okay.
A'dan B'ye,
A to B, okay,
C'den A'ya,
okay,
C'den B'ye,
okay,
A'dan B'ye,
okay,
A'dan C'ye,
okay,
B'den C'ye,
okay,
B'den A'ya,
okay,
C'den A'ya,
okay,
B'den C'ye,
okay.
A'dan B'ye,
A to B, okay,
A'dan C'ye,
okay.
B'den C'ye.
Perfect. Well done. Number of moves is now the minimum number of moves. Okay, so let's change the screen share again to Xcode so that we can look at the code again. Everyone, please focus on this now so that you understand the solution, that you're sure that you understand this solution very well. Thank you very much, Ayşe.
Ne demek hocam?
I hope this was helpful for you as well, for everyone. So can you all understand the solution? It's very important for me.
Hocam, I have a question.
Yes. Can you also say your name?
Jana, I am
Okay,
Jana.
Jana, okay. it's difficult for me to understand which one is okay.
Hocam, so how did we like, okay, this code worked, but how did we implement the idea that a small block cannot, a big block cannot come on top of a small disk? Like, how did we implement that here?
Great, but we didn't really care about that one for now, like, because the idea is, like, if you look at the way we implement this problem, so we first move the top 4. So we know that during this entire operation, the biggest block is already in place. Like it's already sitting in tower A. So we only ordered it to move the top 4, which are all smaller than the bottom. So there is no way we will break that rule. But in order to move that 4, we say, like when you do this recursive call, it will say move the top 3. Again, in that case, you are always making sure that that guy, which was larger, still sitting there. You're only playing with the smaller ones. So recursively, you can only move here. You can only move the top disks, right? So, and those top disks are always the smaller ones based on the way you define the problem. So it's naturally embedded in the solution, I can say.
Oh, okay. Thank you, Hocam.
Just you should think a little bit more about this, like especially in the game. If you do this a lot of times now, then you will understand like how these are automatically handled in the solution. And now, if you like, this implementation is not really important. If you understand the logic, like if you understand the logic of moving, let's go back to this this thing here. So let's
Hocam
say,
bir şey sorabilir miyim?
of course. Can you also say your
Türkçe
name?
olarak ismim Safiye.
Okay,
Türkçe olarak anlayıp anlamadığımı bir size sorabilir miyim acaba?
of course.
Şimdi bu kodda biz büyük olanı küçük olanı az evvel Can arkadaşımız da sormuştu. Onu belirtmemize gerek yok. Çünkü ilk hareketi hep küçük blokla yaptığımız için o recursive olarak onu yapmaya devam edecek kod içerisinde.
Yeah. So if you think the logic, like, can you all see the game now here? So,
Efendim?
can you see the game window, Mathis Fun window?
Evet, evet.
Okay. So, like, if you look at here, the idea here is, again, we want to move this 5 to tower C, but what we first say is move this top 4 to tower B.
Evet.
And this problem, by definition, the top one, if you separate this as 2 parts, the top one, which is larger than this oldest 4, will stay here until you move this. So we won't even touch this top one. So this can never be on top of the other guys. So you are saying first move this 4 to here, then move this bottom one to the right hand side, right? And then move this 4 back on top of it. So in this 3 steps of solution, there is no way this one will come on top of this. And in the next phase, if to move this 4 to here, you're redefining the same problem. So in order to move this 4 here, you are saying that you will move this 3 to here temporarily, and then you will move this like, you should forget about this bottom one for now. You will move this 1 here, then you will move this 3 back to here. Also in this definition, you're always first moving the smaller ones to the desired location, then you are moving the bigger one, and then you move the smaller one back on top of it. So in any part of this definition, you never disobey this rule. It's always you move the smaller ones first. Okay?
Hocam bir şey sorabilir miyim?
Of course. Can you also say your name?
Murat.
Okay.
Bizim bu implementation'imizde tek sayıyı deneyelim mi?
Of course.
Orada da
You mean in the software? You mean here in the code?
Evet. Yani kodu tek sayıyla çalıştıralım mı?
Okay.
Mesela 6'yı 4'ü denedik hep. 3, 5.
Okay. Do you expect a problem when it's 5? So now this is the solution. Of course, there are more steps. So So can you see the solution here?
Evet, yo, doğru çalışıyormuş.
What?
Doğru çalışıyormuş. Evet. Yani tekler C'ye aktarıyoruz önce. Çiftlerde de ikinci tower'la başlıyoruz ya.
Yeah. This will always produce the solution with minimum number of moves. It's naturally the optimal solution. Okay. Any other questions?
Hocam ben bir şey sorabilir miyim?
Of course.
Hocam şimdi biz kodda hep n-1'i yaptık ya.
Okay.
Bizim yaptığımızda n olan yani 4. 6. artık kaç verdiysek onu ne zaman yerini değiştiriyoruz? Kodun algoritmasında orayı tam kafama oturtamadım da.
I really did not understand where you meant, but let me share the screen again so that you can tell me. Share screen. Okay. Can you say it again? I really didn't understand what the question is.
Hocam şimdi fonksiyonun içine girdiğimizde if'in altında Hanoi n-1 diye giriyoruz ya. İşte source aux destination diye.
Okay. Okay.
Şimdi biz hep n-1 yaptığımız zaman
Okay.
n'inci olan yani diyelim ki 5 verdik. 5. olanı ne zaman hareket ettiriyoruz? Kodu ben
This is the step. Like this one moves top 4 from A to B. This one moves the bottom one from A to C. Then this one moves this 4 back to destination. So these two are just the transition steps. Like this one moves top 4 to auxiliary. Then it moves the bottom one from source to destination. Then it moves from auxiliary to destination again.
Tamam hocam anladım. Teşekkür ederim.
Okay.
Hocam bu stepleri kağıt üzerinde yazmadan anlamak çok zor. Çünkü ilk recursive'den sonra 2 tane daha statement var ya. Printf'le bir daha recursive.
Okay.
Mesela onlar n1 olana kadar çalışmayacak. n1 olduktan sonra printf sürekli çalışacak. Yani o biraz da fonksiyonların çalışma şekliyle alakalı da kağıt üzerine denemeden kesinlikle çok zor orası bence.
Okay, but I believe you can all do this. Okay,
Ben yapamamıştım.
yes, I really understand. There are some little difficulties, but I know you can all handle this very well. It's not a big problem. Okay, so please practice recursion. So this is something you should, like a skill that you should be having like in your skill set. This is something very important. Okay, so we will do a quiz now. Can you all turn on your cameras? That is the bad part of this class, but at some point we will have quiz in each lecture.